This is experiment 4. We're going to be looking at the small angle approximation for the period for a pendulum. So please read through the lab instructions before watching this video. I will record the data and record that on the board here, but also record that on a sheet that I will be sending to you as a PDF. So let's take a look at this. Here we have our setup. This is a pendulum bob that is suspended. This one is at 1 meter, so it's going to be the first one that we do. But before we start that, we should remind ourselves of the equation for a simple pendulum. Now, for a simple pendulum, we make the approximation, and I'm not sure that you can see this, that the angle is small enough such that the sine of the angle in radians is approximately equal to the angle. Okay? So if we do this at a small enough angle, we say that this equation is valid, or this equation is a good approximation. Now, there's a much longer expression for the period that has additional terms to this, but those terms pretty much go close to zero, or they approximate zero as the angle gets small. Again, if you look back at the lessons, you can actually see where we solve for the period for the small angle approximation, and we solve for the angle other than the small angle. It just becomes this big, ugly, multi-term. Actually, it's an infinite series of terms. But again, this is perfectly fine as long as the angle is kept small. Now, the other thing that I sent is the sheet that shows the angle in degrees, the angle in radians, the sine of the angle in radians, and then finally, percent difference between sine theta and theta. In the experiment, the first thing that they ask you is, and I've done this for you, at what angle does the difference between sine theta and theta become greater than 5? And you can look at this chart and see that at 32 degrees, I have the wrong answer there. At 32 degrees, 32 degrees, the difference between sine theta and theta becomes greater than 5%. And what that's telling you is, as these two begin to diverge, as these two values, in this case, 5% is not a huge difference, but become different enough, this becomes less of a good approximation. Okay, so that's part 1 of this right here. And again, to remind us that we are doing the approximation, the small angle approximation. Okay, let's do the first experiment. And what I'm going to do is I'm going to use my phone as a timer, and I'm going to set this in motion. Now, we don't want to have this go back and forth more than about 5 degrees. So we're going to use a protractor right here and sort of estimate. Okay, so I only want to pull it back out this far. It doesn't look like the pendulum is moving very much. Okay, just a little bit more. Now I've got a good 5-degree oscillation. So I'm going to time this, and I want to do 10 oscillations. This will allow me to basically divide my value by 10 and reduce the amount of error that I have. When I time this, I always have some error. If I do 10 oscillations, the amount of error that I have becomes 1/10 as large for 10 oscillations than a single oscillation. So I'm going to wait until it comes back here. Start. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 19.9 meters. I'm sorry, 19.9 seconds. Okay, does that make sense here? Think about this. We have 1 meter divided by 9.8. That's roughly about 1/10. You take the square root of 1/10, you get about 0.32. 0.32 times pi, roughly around 1. 1 times 2, well, that looks like my 19.9 seconds for 10 oscillations is roughly about 1.99 seconds. I'm pretty much where I want to be there. So I'll put my first answer here, 1.99 seconds, okay? Actually, I'm putting for 10 oscillations first. So this is 19.9 seconds. 10 oscillations, divide by 10, 1.99 seconds. Okay. So that's the first part. The next part asks you to do it at 10 degrees. So I'm going to increase my amplitude just a little bit. So I'm going to stretch this out. Again, make sure my 90 degrees is equilibrium. So it's just out by about 10 degrees. Okay, I've got a good 10-degree oscillation here. Ideally, the pivot point should be right at this hole here. I can't quite get my protractor up that high, so let's do a little bit of guesstimation here. Okay, we're going to start this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this time I got 20.08. Okay, 20.08. It's going to round that up. 20.1 seconds. I'm going to assume I can't really do timing much better than about a 10th, so I'm not going to carry anything beyond that. And this is 2.01 seconds. So there's not much difference between the two measurements that I did, okay? And they're both around where they should be theoretically, all right? That's going to be left up for you. You're going to have to actually do this calculation again for 1 meter, g being the acceleration of gravity, 9.8, and make sure that your theoretical matches your experimental. Do a percent error. The theoretical is supposed to be accepted value, and see what kind of error you get. Again, you're going to get a very low error for this type of measurement. All right. So now I'm going to adjust the height. I want to use a different height. I'm going to use 0.5 meter here. I'm not being very careful here, but I set this such that the center of mass is, oh, go a little higher than that. Center of mass is at the distance that I want. Yeah, let me just take a look in here. Excuse me. It's allergy season already. Okay, we're going to set this in motion, same way that we did the last time. And we're going to see what we get. Now, think about our expectation. We're at 1/2 of a meter, okay? We basically reduced what was under the radical sign by a factor of 2. I don't even have to do the calculation here. Think about this. The last time, we should have gotten about 2 seconds for a theoretical, okay? You calculate something more precise than that, but I'm just doing back of the envelope calculations. If I cut the length in half, I reduce what's under the radical sign by a factor of 2. But the period will only change by 1 over radical 2. Okay? Because again, you're under the radical sign, I'm cutting this in half. So if 2 is my time for 1 meter, okay, I can divide that by the square root of 2, and I would get about 1.4. Okay? We know the square root of 2 is 1.41. Again, I would expect about 1.4 seconds. Let's see if we get that. Again, I'm going to start this in oscillation. Okay, it's about a 10-degree oscillation, just like the previous case. I'm going to time this once again, so reset. Notice it's moving faster. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? 14.3, not bad at all. 14.3. So here, I get 14.3 seconds for 10 oscillations. I divide that by 2, 1.43 seconds. And that is my next case. Now this is important. We're testing this equation right here. And this equation tells us with a small angle approximation, the only thing that's going to make a difference is length. Okay? Angle doesn't really influence the period here. It's not contained within the equation. So we see that we change the length, and very clearly the period changes, and by about the amount that we expect. All right? So now I'm going to take this off. All right, I'm going to come back to this in a little bit. This, by the way, is 23.3 grams. Right? I'm going to replace it with a 5 gram, approximately 5 gram, wooden bob. And I've got to be very careful here that I repeat the experiment exactly the way I did last time, changing only the variable. This. Changing only the variable of mass. Okay. What's my hypothesis? Well, mass doesn't appear in this equation. So should mass affect the outcome? No, I should have the exact same result that I had before. So I'm going to set this in motion again, keeping everything exactly the same. Also 10 degrees. Okay. I'm going to go ahead and time this. And you can see that's pretty much moving at the same rate as the last one. Okay, 14.27, so 14.3 again. 14.3 seconds, so 1.43 seconds for one oscillation experimentally. Okay, so this seems to hold up pretty well so far. Everything we've done indicates that that's a valid equation. Right? I'm going to go back to this bob again. And once again, string this at the same level. I've got to be really careful here. I'm getting exactly the same level as before. Just a little bit. All right. Perfectly at 1/2 of a meter. But now I'm going to do this at 40 degrees. This equation is only good for small angles. By increasing the angle, okay, I'm starting to get away from this small angle approximation. Because if we look at the sheet, at 40 degrees, my difference between sine theta and theta is 8.25%. So my expectation is that the value that I get are actually extra terms that are attached to this. Those terms are not going to be close enough to 0 to be ignored. That it's going to have some impact on my period. Okay. All right, 40 degrees, all the way up here. Okay. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. Okay. So it's not a huge difference, okay? My time is 14.8 seconds. Okay? So that means that my experimental value for one oscillation is 1.48 seconds. Okay? Now, that's not large, but as you can see, compared to the 1.3, I'm half a second more. Okay? Small angle approximation still seems to work okay. I'll do the exact calculation right here to find out what that is. All right, so what am I going to do? I take 1/2, divide that by 9.8. That gives me 0.0510. Okay? Now I'm going to take the square root of that. Okay, square root. 0.50102. Okay, square root of that is 0.22587. I multiply that by pi, 3.14159. Multiply that by 2. That'll give 2 times this. And here is the theoretical value. Okay? Theoretical value, again, for 1/2 of a meter is 1.42. 1.42 seconds. So that's very close to my experimental result that I have here, when I had the metal bob at 1/2 of a meter, and here, when I had the metal bob at 1/2 of a meter. I'm only off by 1/10 of a second. The 1/10 of a second represents probably the error in my reaction time. In terms of the larger angle at 40 degrees, however, that difference is 0.7. So if I take 0.7 and then divide that by the theoretical, 0.7 represents the difference. Divide that by 1.42. Okay. I get an answer that doesn't make sense. I'm sorry, 0.07. I get a 5% error. Okay? Really sort of follows what my expectation would be. The difference between sine and cosine at 40 degrees is roughly about 8.5%. So, you know, my error in this case wouldn't necessarily be proportional to the error there, but it's 5%. It's much greater than the error that I had with the other ones. Again, when you actually calculate the percent error for each of these, you will find that you're right around 1%. All of a sudden, we jump to a 40-degree angle, and our error has gone from 1%, which is really, really good, to an okay 5%. All right? So once again, here's the equation that we're testing. We're testing the small angle approximation for a simple pendulum. Okay? It states that only the length of the pendulum, okay, only the length of the pendulum will affect the period. Yes, acceleration of gravity will affect the period, but I can't travel to the moon or Mars to change the gravity. So that's pretty much going to be a constant for the experiment. And as we saw, even when we changed the mass of the pendulum bob, the period really didn't change by any appreciable amount. Okay? When I changed the length, yeah. Okay? The period changed by the square root of the length. I cut the length in half, the period changed by the square root of 2. Okay? What can we say about the small angle approximation? It's very good as long as your angles are small. 5 degrees, 10 degrees, it worked fine. When we get up to about 40 degrees, this approximation is not horrible, but a 5% error indicates that it doesn't predict as well for this very large angles. Okay. Simple pendulum.